Hello everyone. Today we'll talk about the solution to the problem find champion 2. This problem is actually very simple. It has a simple solution that's simple to code and simple to understand. So I think this is a nice opportunity to focus on this problem's statement and maybe on how the statement could look at first and how we could refine it by asking some questions. Because the basic idea is that there are some teams. We know that some teams are stronger than others. And we are interested in the strongest team, the champion of the tournament. And of course, since some teams are stronger than the other, it's very natural to think of the situation as a graph. But can it be just any graph? Well, not really. And this is probably the first clarifying question that we can ask, is for us to be able to determine this one being stronger than another and determining the champion, it is very useful if that graph has no cycles. So if it's a DAG, directed acyclic graph. Now in the real world, probably between teams there can be cycles. It can be that team A will typically beat team B can beat team C, and team C can beat team A. But it is a simplification. Situations like this don't happen. Or maybe we only have edges where there are really, one team is really much stronger than another, and there is no possibility of cycles. But this is the first maybe clarifying question, that this should be a directed acyclic graph. And we want it because then we can be talking about what is called in mathematics a partial order, and a set that's partially ordered is called a poset. And the idea is just that a partial order behaves as an ordering, where things can be bigger than other things. But it's partial, so maybe some things are not comparable with each other. And this is the crux of the rest of this problem, of the rest of this statement. Because if somebody were to just tell you who is going to be the champion of the tournament, then if you know something about partial orders, or if you think about the situation that we're given, there can be situations where there is a team such that there is no other team that is stronger than that team. This is even given here at the statement, but maybe this could be an answer to a clarifying question. But there can be multiple such teams. Notice that if all the elements were to be comparable, and we have only a finite number of elements, then we would have the biggest element. Because, for instance, we can just start at any team we want and find any team that beats it. If no team beats it, then that means that it beats every other team and it's the strongest team. If some other team beats it, we move to that other team, and again we find a team that beats it. And since there is only a finite number of elements, we will reach a team that beats everybody else. But in this case, it's possible that by performing this operation, we reach a team, okay, nobody beats that team. So that team can be the champion. There is no team that's stronger than them. So for instance, we can say that this beats this, we can say that this beats this, and whatever, maybe even this beats this. But those two teams, nobody beats them, and we don't know how to compare the two. We actually don't even know how to compare these two, but this team will definitely not be the champion because somebody beats them. This team beats them, right? So there can be multiple teams that are not beat by any other team. Now in mathematics we would call these elements maximal elements. They are maximal because there is nothing bigger than them. But they are not the biggest elements. They are not, the way I was taught, the maximum element, because we don't know if they are bigger than any other element. And this is perhaps the crux where somebody who's not that well versed in mathematics might have difficulty grasping, is the situation where there can be no, it's possible for there to be no biggest element, no element that's bigger than all the others, but for there to be elements that no element is bigger than them. And in fact, if this is indeed a directed acyclic graph, we would have at least one such element. Okay, so all those divagations and just talking around this problem, how do we solve it? Well, we see here that an element such that no other is stronger than it. Oh, by the way I'm writing these arrows here is, I think, reverse of what is told in the problem. The arrow is from weak to strong. In the problem, I think it's from strong to weak. It doesn't change anything. We just have to, we can turn those arrows around in our head. So the way we decided, in at least this formulation, is that the element can be this maximal element if nothing comes out of it. And so in our problem, nothing comes into it. and we can just count all those elements. At first we assume that nothing comes into any element, and for every edge we remove one element from the set, and at the end that set, since the graph is directed acyclic, we will have at least one element, because if we have no elements, then from every element a edge comes, so to every element an edge comes in, so if we walk through those edges in the reverse order, we will always have an edge to walk by, so we can just go in circles. This is a cycle, this is not possible in a DAG, so we are sure that there will be at least one team. If there is more than one team, there is no champion. If there is one team, we are told that that team is the champion, even though this is a pretty weird situation to be thinking about, but yeah, this is what this problem is asking us to say. We can do it with sets. We can take the set of all the teams, because we know that the teams are from 0 to n-1, both inclusive. And now for every edge, we don't care about the strong team in that edge. We only care about the weak team in that edge. That weak team cannot be the champion, so we discard it from the set. By the way, we discard it, not remove it, because we don't care if it was already removed. So discard is for situations like this. Remove this element. If it doesn't exist, then whatever. And then if there is more than one remaining team, then there are two teams, such that we don't know that anything is stronger than them, but we also don't know if they are comparable with each other. So we have to return -1, otherwise we have to return any element from the set, but this set has exactly one element, so we just convert it to a list and return its first element.